again back to the machine learning coffee seminar. And now you also probably noticed that there is the question or the information about the event to be recorded, and then please accept that if you also got the recording question there. So it's very valuable that these events are recorded so you can watch them afterwards, and then the people who couldn't make it for this time here can also watch it afterwards. But so it's time to again start the semester with Machine Learning Coffee seminar, and there has been one change in the organization of the seminar. So Professor Sami Kaski, who has been very successfully chairing the seminar together with me for years, well, I haven't been here for years, but he has been chairing it for years, has now retired from this task, and instead we have Markus Heinonen from Aalto University, and he will be now continuing for chairing the seminar together with me from Aalto side. So if you want to say a few words, Markus, please go ahead.
Yeah, so hello everyone. Yeah, so I will be taking over from Sami's side and organizing from Aalto side. So yeah, I will be looking forward to this.
Great, welcome. Yeah. Okay, and then before I will introduce today's speaker, I will remind you that you are allowed to ask questions either by raising the hand also in the middle of the presentation, or then you can write your question to the chat box and I can read it aloud. So Antti, who will be speaking today, is pleased to get the questions even in between or in the middle of the presentation. But then today we will be hearing a talk from Antti Oulasvirta, who is an associate professor at Aalto University, and he's leading their user interfaces research group. And he will be talking to us today about adaptive interfaces, a new look. So please go ahead, Antti.
Thanks, Laura. I also lead the interactive AI program to which this talk is associated, and I'm happy to be here and happy to be the first installment of the series as it's starting again. This is work with many members of my group and many important people at FCAI. We've been working on this for roughly 1.5 years now. Before that, I was working a lot on model-based computational design, and this is sort of an evolution of that to a bit harder problem. I wish I can teach you a little bit about what we learned and show you. So first I'm going to argue why this should be approached in a particular way. And then I'm going to show at the end a technical instantiation. So this is a very much ongoing work. So it's going to be quite rough at the edges. And I hope that you just talk, just ask me a question if you don't get something. Okay, with that, we could start with the main claim of today, which is that adaptation. I'm going to define what that means, but basically adaptation is about changing an interface for the benefit of the user. Should be considered an intervention. So intervention in the way that you go and change something in the person's environment. And you need to take into account the fact that that other agent is also adapting and learning and changing as well. And if you plan your adaptations like that, you have a better success of actually doing something useful here. This is an area that has been studied in applied AI for maybe 2 decades very actively. And there is not a lot of progress in the sense that we would be using very interesting adaptive interfaces. So I'm going to try to bring a new light here from simulator-based machine learning. So that's the talk in a nutshell. First, I just want you to understand why we're looking at this problem. If you think about most of our interfaces, they are not adaptive in an interesting way. You issue a command, you press something, and then something happens. So it's a reaction, action-reaction type interaction, right? And many of the interfaces that we see today are not designed for you. They are designed with some population in mind or some core user profile in mind, and then the rest, which means more or less everybody have to adapt to the interface and not the other way around. And if there's any AI, it's quite limited if you think about it. If you just think about the amount of screen estate that these adaptations are taking, like recommendations or ads, it's quite limited. So we're nowhere near, the full interface being adapted to the benefit of the user. And the issue that we have here is that there are very large individual differences, very large situational differences. Imagine yourself walking down the street with a mobile device versus being at the desktop. Think about aging population who have big difficulties in using their computers. And adaptation could be the key to help everybody get more out of their computers. So this is not a new motivation for this. Is more or less a variation of what has been said for many decades. And I just want to remind you of this goal. So it seems like it's a nice, ambitious application area for AI, right? And of course, you might think now, well, haven't we done this already? We're using recommendation systems all the time. Well, if you think about recommendation systems, they're only, picking you content that you might like. And they're nowhere, there to, for example, help your grandfather, to help use a computer better, or to help you be more productive in the way you use your computer, or create completely new experiences. It's actually just a small subset of the space of adaptations that we could be considering. I want to link this to broader aims of the Finnish Center for AI before I zoom into the problem of adaptation. So AI, so FCAI has taken these three main objectives: understandability, data efficiency, and trust and ethics. And the key vision, is summarized as real AI for real people in the real world. And this sounds, when someone says that, he says that this may sound a bit naive, but we're serious about it. And I'm going to be talking about how to make AI understand people. And as an application area of that, I'm going to talk about adaptation. Because I think that for adaptation, you need this capability. And it's an interesting micro world where you can study this problem. But why study artificial human understanding in general? It's because we need AI that can work with us better, that can be trustworthy, that can explain itself to the user, and of course to be efficient as well. When you deal with humans in the loop, from just a few cues, just like we do in human-human interaction, you need to make some pretty far stretching interpretations. And I think the key is this missing ingredient of understanding people. And this is interesting that much of the AI community is also looking into this direction and realizing that this is a problem. Just yesterday, I took this on Twitter. Gary Marcus is a big personality in AI debates. Coming more from the cognitive sciences perspective, he's been, let's say, championing criticism of deep learning as insufficient for certain purposes in AI. One of them being understanding people. And he's writing here in this tweet that we don't need deep learning, we need deep understanding in order to make trustworthy AI. So it seems like some of the other parts of the community are also going to look into this direction. Well, luckily we already been there for at least 2 years, so we have some results already that I'm going to show later. So let's take a step back. So of course, if you want to create AI that understands people, you could maybe first look at, well, how do people understand people? And I collected 2 things here that are important that come from social psychology. Number one, that social inference is important. So we make these inferences about each other all the time. What would be your belief? What kind of emotion do you have? What do you mean by that communication act? And of course, if you have that capability that is basic to our interaction broken down, just like in autistic children, then you have some serious issues. And if you think about intelligence outside of this kind of problem-solving intelligence that we tend to emphasize in AI, if you think about social intelligence, emotional intelligence, they have deep links to this social inference capability. And of course, once you have a representation that you learn from this kind of interaction and social inference, of another person, you can use that to actively intervene, for example, do something or make yourself more understandable, communicate. You can guide other people's attention, take turns, just like the parent and the kid there in the picture. Now, there's a point of divergence. Like, I'm not claiming that we should replicate human-like understanding of people in AI. I'm not actually in that camp at all. So, so we have a different stance to how we're doing things. And instead, we're coming from a science, behavioral science and social sciences, and implement predictive models and simulators, but they don't necessarily replicate how people, although how people think about each other, although they may have some similarities, but that's not the main aim. So moving on to describe what's required of an agent that tries to adapt or understand another agent, especially if that agent is a human. Here's a key problem. If you think about that kid using the tablet, let's say that the kid makes a tap, and that tap is the only observation that your AI agent has. Well, what on earth was the reason behind the tap? Was the kid exploring the interface, or was that part of was that an error? We have a lot of noise in our motor systems, and it might have been a slip. Was the kid intentionally tapping an element to start that command, or what was behind that simple act? This is, of course, just a small corner of the complexity of inferences that we should be able to do as an adaptive system. Right? So I'm claiming that in order to understand a person as an AI agent, you need to be able to capture certain essential aspects of their thinking that drive their behavior. And these constructs come from behavioral or cognitive sciences. They are constructs like goals and capabilities. And these factors should not only be, like states, they should also be linked to mechanisms that link those states to future actions. How is that person going to act in the future? Otherwise, we cannot predict what's going to happen if we intervene to that person's world in a particular way. I don't know if you follow the application areas of AI, but one of them is affective computing. And for a long time, it was happy with this state inference problems, just inferring a single state, like is this person happy or is this person sad, from, let's say, supervised labels. And that wasn't really useful because they didn't have knowledge of, so what? What can you do with this knowledge? So you really need to get those mechanisms somehow as well. However, those mechanisms are really, really difficult to infer from data only, right? Because if you just have that person and you have some tap data, well, how on earth can you say something about that person's more deeper psychological mechanisms, right? And that's, by the way, key reason why we're ending up not with data-driven machine learning, but a simulated-based machine learning. Okay, so now we come back. So I've been explaining how we approach understanding. And now we come back to the problem of adaptation. And this is an interface that my wife needs to use, or this is actually an English version of the same. It's an Apotti health informatics system that they use, or patient system that they use at the KUS. And it's just absolutely horrible. And it would be great if something good could be done for that. For example, adapting to the particular doctor, or the role, or whatever the case is on, or so on. It would be helping a lot in terms of productivity and so on. Now, so what's this problem of adaptation? You can formulate that as a decision problem, and that's really natural for any application of AI, because AI, from one sense, is an agent, and what it means to be an agent is that you take action on your own. And for that you need to decide something. So what are those actions? You can, in a broad sense, in adaptation, you can change anything, right? You can change the full information architecture. You can change some colors or labels or whatever, anything that you see here, anything that you can interact with here. And the observation data can be anything that you can sense from the user. It can be log files. It can be some sensor data from the mouse, or I don't know if you have physiological sensing or whatever. And the objective should be something related to the end user. And this is, of course, the key challenge, because some of those objectives are really hard to sense, right? You cannot sense them directly, right? They are latent. You know, for example, usability is not something that you can directly sense. You have to infer that somehow. Experience is not something that you can directly sense. You have to infer that somehow. And of course, you'd like to improve the use, those aspects for this individual. However, these rewards or these objectives are latent, so they're not observable directly from the user data, and they're changing as well. As we know, people are adapting, they're learning, and so on. So now this characterizes why this is a really hard problem. You just think about those action space. Think about changing one color on the display. Well, that means that you're going to change the whole perceptual experience of everything else as well on the display. So everything affects everything on the display in terms of when it comes to colors and sizes and all these perceptual primitives. So, you know, it's a huge combinatorial problem. Even if you make one change, it's going to have lots of, you know, downstream effects. Good. I hope I have now characterized the problem of adaptation to the level that now you're with me, and we can start looking at how to approach this problem. If you have any questions at this point, please ask. I cannot, by the way, see your hands, so then Laura or Markus, if you can moderate this, and then.
Yes, of course, I'm watching all the time, so don't worry.
Okay, good. So let's move on. So I want to characterize and give you an illustration of why this adaptation is such a big problem. And I take an everyday example. So let's say that you're buying a present to a person who's not a very close one to you. Let's say that you've seen that person a few times, and now you need to buy a present, and you go to the store, and you have, you know, everything in the store is a possible gift, right? So how on earth can you pick a birthday present? So why am I making such a big or, you know, such an esoteric example? The reason is that you can think about this birthday present buying from the perspective of that being an intervention. So you know, not only picking something, right? You're picking something that the other person is going to use. It's going to have an effect on that other person's life. So in order to then design your gift like that, you need to, closing the window, you need to engage in inference. You know, what might that person want? The second thing is also tricky. You may also need to engage in counterfactual prediction. So you've never been in this situation before. You never bought this present to the person. So it's not in your training data as a person. But you should decide, you know, how good would this gift be when it's actually used, right? So you probably engage in some sort of mental simulation that, okay, the person is doing some dishes with this new thing, or dishwasher or whatever, or is enjoying Netflix. And, you know, that's going to be your objective function then. And of course, planning as well is involved. For example, if you buy Netflix credits, well, you need to ensure that that person has a suitable internet connection and doesn't already have the Netflix and so on. So it's illuminating why adaptation is, when it's designed as an intervention, is such a tricky thing. So next time you go to buy a birthday present, you can think about my talk. So coming back to those points, adaptation, if you design it as an intervention, requires a bit of speculation. I have to speculate what would happen if I took this action. So what would happen if I changed the elements like this, if the information architecture was like this, or if I bought this birthday present. And that's difficult. That's difficult because those would-bes, those future state of affairs, are not necessarily in your data set. You've never seen this before. And this makes it really, really difficult for purely supervised learning algorithms to take that leap and speculate about what could happen. And that's where you need some stronger mechanisms like causality and simulation can offer. This is, of course, an area. Adaptation is an area that has been studied a lot. And as I said, there's this whole area which is called intelligent user interfaces that's been looking at for 3 decades, depending on how you count. And it builds on the problem of design that has been at the core of human-computer interaction research. And it started with I think the first scholarly publication on this topic was by the psychologist August Dvorak, who designed the Dvorak simplified keyboard that you may know, that's on the left. And he was saying that psychology should be the basis of design choices, but then he couldn't really tell how we can solve practical design problems because they are so immense. So what he did when he designed the keyboard, he basically tried manually different layouts. Then coming from optimization, there was Rainer Burkhardt, and who was saying that, well, we can use those models, if we have models, as objective functions and do combinatorial optimization. Well, unfortunately, combinatorial optimization is not sufficient for solving this problem of adaptation as an intervention, right? Because it doesn't do planning. So this doesn't really yet solve that problem. And then there were other people. If you think about the development of AI, we've been trying every mainstream AI approach to this problem. At some point, there was a strong influence from cognitive modeling and cognitive sciences, and the idea was that cognitive models can predict user behavior. Why don't we plug in cognitive models into our adaptive systems? Then after that, we tried rule-based systems, and right now, as I said, everybody has been trying supervised learning, but because it's sort of victim of the training data set is not able to take that leap that we need for that speculation step. I just want to show you how these rule-based systems really look like. And I gave a keynote at one of the conferences that looks at these rule and logic and heuristic-based AI systems, adaptive systems, and sometimes they want to engage in like hand coding a full ontology of the world that might look like something like you see on the display, and they would have another set of rules or logic that would then deal with reasoning about that world. So if there's a particular condition that is expressed, then act and adapt the interface like this. And as you can imagine, that doesn't scale up really well. As horrendous amount of work and really rigid systems that you build with that. And critically, I mean, they don't really estimate the value of an adaptation to person. I mean, that's sort of hand coded into the rules. So the designer puts it in, and if that rule is okay for that individual, then it's going to be okay. But maybe you need a very large number of rules and a lot of foresight in order to develop a rule-based system like that. So sort of the same story as we hear from rule-based systems in AI in general also happened here.
Antti, now there's a question.
Yeah, please.
Antti Hyttinen is asking, what is the fact this is counterfactual respect to? Why is this not just prediction?
Okay, I'm using this term to flag it as something special in the sense that we're speculating about a world that also depends on our action. Okay, so it's as opposed to like weather, probably, you can talk about that as prediction because it's going to happen no matter what you do. But if you think about counterfactual world, it's going to be affected by a choice. So if I'm going to make this choice like this, then the world is going to be like that. That's my understanding on this. We can have a discussion with some people who probably know better than I do. But this is the meaning I've been using for this. Okay.
Thank you.
Moving on. So why don't we use reinforcement learning? And of course, indeed, we could be using that. So basically learning a mapping between actions, good actions and states from experience only, right? And that's model-free reinforcement learning. And here's an example of socially intelligent robots that are able to do some simple handshaking or that kind of gesturing to people using deep reinforcement learning. And there are two issues. First of all, they're really brittle and are not really able to do this counterfactual part at all, right? Because if you never bought this this birthday present before, how can you take that leap from your previous knowledge and buy it for this person? I mean, these kind of things would be very hard for them. So unless it's somehow encapsulated in the training regime that they went through, then it would be really hard to take that leap. The other one is it's really inefficient, right? You need millions and millions of trials. And probably people don't have enough patience to deal with millions and millions of trials with stupid robots. Well, why don't we just show the model to the user? Why don't we just show how the adaptive system works, like the rule-based system, and then let people change the rules and thereby get the kind of adaptation that they want. Well, that's probably not going to work. It's sort of common sense that if you just show to a regular person, a big, I don't know, decision tree or rule system that would be a sort of simplification of the underlying complex system, it's still going to be overly complex. And now there's some evidence now supporting this very common sense notion that people are not going to be interested in that kind of control. There are some empirical studies suggesting that it would be detrimental to expose these kind of model internals. It can overwhelm people. Okay. Well, coming back to this this idea that I presented in the gallery, why do we plug in some cognitive models? Here's an example of a cognitive model. One of the issues there with the classical cognitive architecture-based models was that they don't really adapt. So if you think about making or sort of speculating about what would happen if I made this intervention, then these models don't really give you that because you would have to hand code certain procedures into the system or the model that would then allow it to adapt to that. But then, because there's such a big number of this adaptation, that would require a big number of rules, then this didn't really scale up to that well. So, I've been driving this to the corner. Now I'm supposed to tell you how we should be doing this. And I don't know if there's any question at this point. It's been quite quiet, but I'm happy to take some questions. Okay, so let's go to how we approach this at FGAI. And we use simulator-based machine learning to try to attack this problem. This is the part where I'm entering sort of the ongoing work territory. So I really welcome your comments at the end. If you have suggestions on how to do this better, please approach me. So I'm going to lead you through some thinking behind our approach. Number one, when deep learning made its big breakthrough, then there was a discussion from psychologists and cognitive scientists on, well, how could we make AI agents think more like people do, right? This is not the same as what, the problem of understanding, or not the problem of adaptation. But how can we make agents that think like people do? And this is a really interesting piece that is published in one of the most prestigious psychological journals called Behavioral and Brain Sciences, and it's called Building Machines That Learn and Think Like People. And they had like 3 takeaways. Number one, people use causal models of the world that then help them explain and understand the world, rather than merely doing like pattern recognition problems. So that's helping them to take this leap that I mentioned. Number two, in particular, they have intuitive theories of physics and psychology, intuitive in the sense that they don't learn that from the books, but they learn it by experience, and they may have some like gaps and issues there that are not compatible with scientific understanding, but that they nonetheless use to support and enrich the knowledge that they learn. And then number three, they compose or put together facets of different representations like that together in order to, and also have metacognitive abilities to learn in order to then generalize this kind of knowledge to new tasks and situations. Now, as I said, this is about machines that think like people. This is not about understanding people, or that they have a lot of commonalities, obviously. So this was one of the sort of inspirations to our work and approach. So simulator-based machine learning, what was that? In our case, for adaptation, you have this kind of Greek opera where you have an interface that is listening to a planner, and that's the AI agent that is solving this adaptation problem that I showed. And it's planning to the future. It's planning possible changes to the interface, as well as the joint changes to the user, with the help of the whisperer, the simulator on the left. Right? The simulator whispers some values and estimates to the planner, who's then using that as the basis of navigating and choosing in that big design space.
Hey,
yeah.
sorry, Antti, again, now there's a question.
Yes.
You talked a lot about understanding people, but one big missing part would be to make itself understood by people.
Yeah.
What's your take on that?
Yeah, that's a very good and very much interlinked, you're right. I think they're closely intertwined. If you think about me understanding you, you understanding me, it's not like, in regular interactive situations, it's not like there's a big asymmetry, but then this kind of symmetrical understanding emerges via interactions, right? I take an action, you take an action, and we form a common ground. So if we're able to do this kind of systems that I'm showing, then by virtue of making or understanding the user better and taking better action, and the user will also start understanding the system better. So this is my hypothesis. But there's another aspect to this, which is of course that we're using simulators that have some theory ingredients that come from behavioral and social sciences. So by design, they have some elements that can be exposed to the user in such a way that the user can understand better the AI. Right? We're not really at the moment working on this, but that's by virtue of the approach that we're following. Okay, moving on. So this is an overview of how we do things, and this is ongoing work with Andrew House and Jussi Jokinen. We've been trying to formally describe this, and there's a formalism behind this that would be captured in multi-agent systems. And in a way, this is an instance of those, where you have, this is the human user, and it's a sort of, human user is a sort of biological data generating process. We don't know much about that, but it's a big lump of meat, which is internal process. It's affected by an external environment, right? But it's also affecting and observing a joint environment between the system and the user. Now, we have a simulator that can try to, so we use the same color because the simulator is trying to mimic or model the user behind this barrier of the joint environment. There's the joint environment, that's sort of barrier. You can never access truly what's inside of the user, right? You can only see what the user is doing in this joint environment. And we can try to infer, we can make model selection and parameter inference based on whatever we observe that's happening in this joint environment. Now this adaptive system has its own design criteria that can be completely different than what the user is doing. But nonetheless, it has the simulator in its disposal. It can use that to ask questions, what would happen? So this is the speculation part. What would happen if I was taking this action? What would be the consequence to the user? And then the simulator gives a sort of prediction that, okay, this is what would happen. And then it can then bring it back to the world by acting there in the world, can observe. So it can make experiments as well. It can, it can try something out. It can try something out not only to improve the joint environment, it can also try something out in order to learn and make a better simulator, better model. So that's called experiment design. So it can jointly be optimizing the design or the environment as it's also doing experiment design, so learning from the user maximally. Okay.
Sorry, Antti, there's a question again. So when humans adapt to an interface, they often don't expect it to change. Yeah. So wouldn't any adaptive interface in a sense come in the way of human adaptation, even it's a superior fit? The user now need to predict how the UI adapts while working with an interface in addition to interference from previous representations of the UI.
Oh, this is a brilliant point because it's preempting what I was supposed to say on the next slides. But yes, so there's this, like this difficult oscillation. You change something and then the user changes, and it might never stabilize. And you can try to avoid that if you have a model of how the user will change. So if you have a model of how user learns and user changes, then you have a better chance of avoiding that. That's excellent because that's the core of what we do when we do models. Now I want to jump into the research challenges. I use the remaining time to talk about those, and then I show the example. So there are three research challenges that we work on in our teams. Number one, we want to do better models of human behavior, and I just want to emphasize one point about it. We don't necessarily want to make the most biologically plausible, most complex model of human behavior. But something that just does the work for our case. So just capture the main sources of variance, reproduce certain empirical phenomena that are important for our case, whatever adaptive interface we're dealing with, make some verifiable predictions in the sense that then you can use that as a basis of this counterfactual reasoning or prediction. And then, of course, it should not be overly complex. So you should, of course, have something that you can fit into the observational data. And then, you know, if possible, it would be great if it was also compatible with existing theories. This is a very, you know, cynical view of modeling as science. You know, we just need to get something that works. Right? So to come back to your question, we assume people are adapting, and in order to do that, we're doing it in a particular way, and that particular way is called computational rationality. And if you know the history of behavioral economics, you know the thesis of rationality and how that was debunked by Herbert Simon, and now this has moved on to current understanding that people can be approximated as optimal adaptations to their own bounds, meaning their internal bounds and external bounds within the knowledge that they have. And you know, when we do a simulator of human behavior, we can try to estimate that core optimality. So if we know something about what they observe in the environment, if we know something about the key limitations that they have in terms of their cognitive capabilities, we can try to make a pretty good guess on how they might adapt, how they might change. And this is where we can use machine learning. I'm going to show, Andrew Hobbs is here, he's one of the leaders in this area of computational rationality and applications. But if you think about this triangle here, this triangle is the space of possible behaviors a person could take. Now, if you know something about the goals of that person, that space becomes smaller. If you know something about the capacities of that person, that space becomes even smaller. And if you know that person's environment, that space becomes even smaller. And then you have only this part in the middle left. And that's called the space of feasible behavior, something that, you know, some rational actor could do. But even, you know, there somewhere, there's an optimal behavior. And that we can now estimate with reinforcement learning. So we formulate a Markov decision process, a model of a person as optimal decision maker given its own bounds. And we try to solve that and estimate that using reinforcement learning. Technically, this is done as a Markov decision process, or what is called partially observable Markov decision process. I'm not going to talk about that today, maybe later. But this is a core work that we do with cognitive scientists. The other part of work is to deal with inference. So if you have observation data, like log data, you need to drive the simulator to a state that corresponds as much as possible with the user. And and we can try to achieve this with Bayesian optimization. This is something that we work with Jukka Korander and Sami Kaski. And the key challenge is from a human perspective, is to find the right discrepancy function of how do you organize this behavioral space when you want to fit those models to fit with human behavior, such that then the parameters might be a good estimation of the user. I had a talk about this maybe last year, so you can look at my slides from that talk if you're interested in how this is done. Now, the last challenge is, of course, you need to plan an adaptation. If the other person is changing and you are changing, well, you need to take into account sort of the regularities of how the human is changing in order to then drive the interface gracefully and gradually into the state where you want to go. So you definitely don't want to do a full-fledged change of the design, because it's going to annoy people. There's going to be very high learning costs. You need to do a bit of planning. So you need to take, you know, step-by-step, you know, changes that are sort of somehow digestible given the status of the user. And this can be done via planning, well, among others, via planning algorithms like the Monte Carlo tree search. This is something that we work on. So now I want to spend maybe 2 minutes to show first implementation of this in practice. So we're working on this problem of menu adaptation. So you take a menu and you have observation data on what the user is clicking, and you plan, as I showed, this kind of adaptive sequence that over time, taking the user's learning into account and taking the user's current skill level into account, then drives the interface to be better for that person. How this happens in practice, you have the Monte Carlo tree search, where we have estimations of values of adaptations that come from simulators. The simulators are simulators of people using menus that follow different strategies. And basically you plan in this tree and you do model-based reinforcement learning, and you pick the best action based on the planned thing. And then you observe again, and you do another set of planning, and there you are. So it leads to this very gradual change that doesn't overwhelm the user. Well, what would those models look like? We have simulator models that come from literature that are about how people serially search a menu, how they might be foraging when they look for a particular label, how they might be using their memory. And those are conditioned by their experience. So the more you have learned about the menu, the more, the differently you'll be using that strategy. They're also conditioned by the design itself. So depending on how the menu is organized, then the strategy can play out differently. Now what we can do is we can look at the rational choice of a strategy. So if the user was rational, which distribution would the user follow these different strategies? So over time, the user becomes more recall driven and less serial driven and so on. And that serves as the basis of the model-based reinforcement learning approach. I just want to say that we implemented, of course, deep learning here as well, that can make it that can help us scale up, so we can compute this in much quicker time, and that sort of where the rollout depth of how far away you plan doesn't choke us. So here are some simulation-based results. A very small menu just to give you an idea of how this could work. If there's a random distribution from where we draw these clicks of the user, then the simulation-based approach drives the average selection time from 4.4 seconds over these two adaptations to 2 seconds. If you have a bigger menu, 15 items, we can get it almost to half with adaptations. And we're planning the sequence of adaptations. Now, there were no empirical results yet because we are right now planning, actually running those studies. So this Thursday is the Kai deadline, and Kashyap Tori is busy running the study. So we get to see if this actually works. It's a very exciting time for me. To summarize, we've been developing this simulator-based approach to adaptive UIs. I strongly believe that this is much better than the existing rule-based and deep learning-based approaches. And it's based on this idea of inferring models and using them as a basis of planning actions. So, and at the core of it, there are models that are partially sharing behavioral and social scientific ideas, and then also learn from data, whether that's, for example, the parameters of the model or some deeper things than it's over here. And that's our goal to. That's our approach to then adapting interfaces for the benefit of people. Thank you. Sorry for this taking a lot of time. I hope that there would be more time for discussion. Then feel free to ping me also afterwards, or but let's hear any questions there. I'm okay. I can stay here later if over time if you have questions.
Well, thank you, Antti. It was really interesting, and I don't think it matters because you already answered quite many questions during the presentation. But then there is. Oh, okay. Sorry, I'm reading. So, isn't it so that this is a new question? Yeah. So do you want to ask it aloud, or do you want me to?
Yes,
to read?
I can ask it myself.
Yes, please.
There might be some background noise because we have some renovations here in our house.
No,
so,
it doesn't matter.
Very interesting. So I really liked your talk. I asked this question earlier about the kind of the system making itself understood, which I find very important. And now looking at your approach that you want to see that you can adapt the user interface, for example, to the needs of the interaction and so on. I find this in a similar way as the former comment quite annoying if a user interface would adapt to itself and then becoming different to what the user is expecting. And I would seem to see that it's more important that a system can really explain itself instead of changing its behavior, or its kind of interface, meaning that if a system can stick to the same interface but instead explain to the user how it is being used, that would be much more helpful from a practical point of view. How do you see that?
Jörg, I don't think that these are like mutually exclusive. You know, in some cases you need explanation, you know, like why do you act like this, and in some cases you just want the damn thing to work, right? And to the extent that annoyance is something that we can model, then of course it can be part of the simulator, and we can take that into account. So what we're doing here, I didn't explain too much, but in the menu case, for example, we can avoid drastic changes. Okay, so we can avoid changes that would cause you to, or force you to relearn the interface a lot. We can make that a controllable parameter. We can say that, okay, I can only approve, you know, 2% more relearning per, you know, 1 hour of use, right? And if you want to have a big change quickly, you can also ask the system, you know, to drive toward the optimal quicker. So that's something that then comes thanks to the virtue of this being modeled, you know, with models that have human-related goals inside of them.
So what would be your take on like a system would detect that there's some kind of conflict or misunderstanding, then it could start explaining? How would you model that? How would you develop such a system that can point, for example, to the part in the menu that you have to click on if you want to do certain things?
So, of course, everything is limited by what's in the model. But if the model had some part that would tap into the, for example, the memory representation of the representation of different parts of the menu or different parts of the system, you know, we can then try to guide the user to look at that. We can make, for example, a highlight, or we can make a prompt asking you to do that. And what's better is that we wouldn't do that naively. We would only make that as an intervention in the light of, you know, what would be the consequence of that prompt or intervention to your present use. So as opposed to like Microsoft Clippy was always making that intervention and saying that, oh, it looks like you're doing this, you know, why don't you do it like that? And you know, like then we can take those costs and benefits of this intervention into account intrinsically. But I mean, there's no silver bullet. You know, whatever you ask in terms of explainability, memorability, you know, you need to put into the model. And that's why this is a truly transdisciplinary approach, in the sense that we work with, you know, people who come from behavioral sciences, social sciences. It's not like a machine learning person can alone, you know, go and solve these problems. This is something where we have to work together.
Okay, thank you.
So there are many questions coming also. Do you still have time?
I have time, yeah.
Okay, so maybe we can take it over a bit, and of course you who are busy can then jump out. But there's first Anna is asking a question.
Hi, Anna.
So would you like to ask it aloud, or do you want me to read it?
I can ask more like extended. What happens if you don't have enough data? Because let's say if you have a lot of data, you can apply all this machine learning. But do you work in situations where there is not enough data?
There are forms of machine learning that don't require you to have a lot of data, right? And you know, like the stronger assumptions you make about the world, the less data you need, in a way, right? And you know, in order to make an interactive system that can, with very few observations, you know, make a reasonable adaptation, you need to have quite strong assumptions about that person, some sort of strong prior about that person. Otherwise, it's not going to work. So you know, that's one assumption that you had in your question, that, you know, machine learning only works if you have lots of data. That's not right. If you don't have any data, you can still benefit from the models, right? Let's assume a system that doesn't have any access to any data. Well, if you have you know, this strong prior, it would have reasonable behavior already on its own, because it's based on, let's say, human theories or human data that you have obtained somewhere else. And what it could also do is that it can adapt its behavior, assuming that the user will adapt, even if it doesn't have any notion about any direct data from the user. So, for example, if you know what is the status of the menu, or if you know how the web page is organized. Well, that's part of this joint environment that I showed, and you can make estimations of how would a rational person, even if I don't know anything else about that person, work in that environment. So you can do already something without data, and that's actually a cool thing that comes with this. I mean, of course, I haven't proven this, but in principle, this could work.
Okay, and then still one question from Rod before we.
Yeah.
Okay, yeah, it was just talking about the adaptation issue and how it's perceived by the users, because when we interact with other human beings, we don't, although they're adapting all the time and you never interact with the same person twice in theory, you know, viewed from a sort of functional behavior, we don't perceive it that way. We think, you know, maybe something I said changed their attitude in that call, or they suddenly seem to start asking me more questions about something. So there's still a sense that you're still interacting with the same agent. And really, if you manage to cut things at the joints, then people aren't going to think this adaptive agent is just changing all the time. They're going to think, oh, it started to explore my wishes in that area, or it started to try and find out more what my context was, and it's got the wrong end of the stick on that. So it's going to be all about, you know, making the right designs of the perception that feel natural to the humans engaging with it, and displaying the state of the agent's reasoning in a consistent way so that you understand more about what's going on. So I think, yes, you're wanting to have things adapting, but they are going to, if you get the design right, then we can use humans as a model. We don't keep thinking we're working with different people, because we assume some consistency and we try and understand what the meaning of the change in behavior is.
Yeah, thank you for that comment. I wish I had a slide where I would explain the different time scales of change in people. You can think about some millisecond changes in your physiology. You can think about some second things that happen in a few seconds, things that happen in minutes, like forming new beliefs, things that take hours and days, maybe like changes in attitudes, they may take, months or years, and changes in personality definitely take years. So some things are definitely changing, fast, like, what do you see right now? How is your, what are the sensations that you're getting right now? And then, there are these different processes that go on. And there's no principled reason why we couldn't, model also those different layers, right? Right now, it's of course out of reach to, do such an overreaching model, right? In practical terms, but in the future at least.
Okay, great. Thank you, Antti, for the very interesting presentation, and also taking the overtime to replying the questions. So we will end the session for today, and then we will continue again next week at the same time at the same channel. Okay, thank you, and see you again. Bye-bye.
Yeah, thanks.
Thank you. Bye.
Thank you.
Bye.
Thank you.